Sir, are we audible?
Yes, sir.
Fine, sir. Thank you.
Yes. Now it's all right. Everything is fine now.
Yes, sir. Fine. Thank you.
A warm welcome to the afternoon session of International Seminar on Indian Mathematician and their Contribution 2022. So here, introduce Sir to the session. Dr. Sriram Chothaiwala Sir, the All India Convener, Department of Vedic Mathematics under the New Delhi-based Shiksha Sanskriti Uttanyas, has been working in the field of education for over 4 decades. Sriram Chothaiwala has been awarded the 10th Madhava Mathematics Award instituted by the Madhava Mathematical Center. Sir is a former mathematics teacher at Amlok Chand College, Yavatmal, Amaravati University, Maharashtra. Dr. Chothaiwala, sir, is currently the All India Convener of the Department of Vedic Mathematics under the New Delhi-based Shiksha Sanskriti Uttanyas. Through various posts in different institutes, Sir is serving in the Vedic mathematics. Sir is a member of Vidya Bharati, All India Vedic Mathematical Council of Mathematics. Sir is Chief Faculty of Teacher Training Program in Vedic Mathematics, has been working as a subject expert at the Art of Living International Center, Bengaluru, to promote the Indian mathematics. Dr. Chothaiwala sir has been national journals. The Varahamihiran's article on Gandha Shastra was recently published in the Springer Journal. Sir holds faculty position at various universities, including Nyasa, Vidya Bharati, Art of Living, JNU, Maratha University, Kalidasa University, and Bhiwani University. He has also authored 6 books on Indian mathematics, and he has written many popular articles in different newspapers and magazines. The University Grand Commission has also aired the 10-episode TV series on Vedic mathematics for the Gnanaranjan channel. So it's our privilege to have you within us on this auspicious occasion. I want to say the journey, the mathematics journey of Sir is like a Ganga river, which begins in minuteness and ends in magnificence. A heartily welcome to you to this.
Am I audible?
Yes, sir, you're perfectly audible.
Okay, I will share the screen now. Allow me to do that. Okay, please check whether my slide is visible.
Yes, sir.
Thank you. To the authorities of university and Department of Mathematics of University, at the outset, I congratulate the authorities for organizing such a wonderful seminar on the occasion of the National Mathematics Day tomorrow. It is my great honor to be one of the speakers, which includes stalwarts like many I know, but many I don't know. So both way I will be benefited by attending this particular seminar. My topic of today's discussion, which I chose for, is some innovative contributions of Mahaviracharya. Let me tell you that this Mahaviracharya is a 9th century mathematician and naturally different from Mahaviracharya of Jain Tirthankar. But before we go to the actual innovative contributions by Mahaviracharya, let me take you to a quick journey of legacy of Mahaviracharya. So what was the mathematics and mathematicians before Mahaviracharya? So as we know, mathematics originated and developed in India since Vedic period. Meghatiti was the first Rishi who elaborated decimal system from 1 to Parardha, in today's language 10 to the power 12, in Rigveda itself. So we have a clear-cut evidence that at the time when Rigveda was in practice or written, or whatever you can say about that Rigveda, the person at that time were well aware of the number system because they are given the names from Eka, Dasha, etc. up to Parardha. Then comes what we call as the Shulva Sutra period. Shulva means rope, Sutra means formula. So they are the geometrical results. Shulva Sutras are primarily written for the yajna purposes. So when any person wants to perform a yajna, he needs to do it on a proper place with a proper Vedi and all the things. So any mistake in that construction, Yajna Bhumi, Yajna Vedi, Chiti, Vedika, etc., may hurt the purpose of the yajna itself. So a very particular precautions are taken to construct. So for all those construction purposes, the Shulva Sutra Grantha are there, and they gives the knowledge of the geometry of that year. So they are called Shulva Sutra. Then comes a period of Panini Chanda Shastra, where Panini has elaborated the mathematical applications in his grammar in extensive way. Then a period of Buddhist and Jaina school comes, which may be roughly said to be 600 BC to 300 AD. Then age of epics and Siddhantas, as they are used to call Surya Siddhanta, etc. And after this, the golden age of development of mathematics in India is started, as it is called a golden age only because from this period, the mathematics flourished in India very extensively. The first of them was, of course, first Aryabhatta, Aryabhatta I, as it is called. Then comes a well-known commentator, Bhaskara I. There are two Aryabhattas and two Bhaskaras. So this Vriddha Aryabhatta, as it is called Aryabhatta I, which is of the 5th century AD. Then Bhaskara I. Then comes all-time famous Brahmagupta, 628 AD. Then in excavation, we found some manuscripts, popularly called Bakshali manuscripts. And those manuscripts tells us the story of status of mathematics in India. In 8th century, 750 AD roughly, a Sridharacharya comes. Up to the age of Sridharacharya, it was a practice of giving mathematical rules or any mathematical principle as a sub-part of the astronomy script. Ms. Aryabhatta has written Aryabhatiya Siddhanta, in which there is one chapter called Ganita Pada. That way, the mathematics was introduced. But Sridharacharya was the first mathematician who wrote a book separately on mathematics, named as Patiganita. And it does not include, or highly, one or two cases include some about geometry, pure mathematical textbook. The credit goes to Sridharacharya, 750 AD, Patiganita name. And then two more Jaina mathematicians are there. One is Veerasena and then another is Virahanka. after in 800th century period before Mahavira. This Virahanka was credited with for discovering what we today call the Fibonacci number, a very famous discovery and very fascinating one. But now all over the world, this credit is awarded to Virahanka. So from Aryabhatta to Virahanka, so nearly 500 years period, mathematics developed very strongly in all the walks of its discipline. May it be arithmetic, may it be algebra, may be geometry, even in trigonometry, even in interpolation, even in the area somewhat like calculus, near to calculus. All these branches start developing in India. With this background or with this legacy in Mahaviracharya has written and a book called Ganita Sara Sangraha. A king of Rashtrakuta dynasty, popularly known as Amogha Varsha, ruled during 815 to 817 AD from a place now known as Malkhed near Gulbarga in Karnataka. I have purposely selected Mahaviracharya because this seminar is conducted by some university in Karnataka. I am daring that way in a sense that I hope that Karnataka people or Karnataka scholars from Karnataka know well about Mahaviracharya. Still, I dare it. So to talk on Mahaviracharya. So please excuse me that way also. So this Mahaviracharya, in the fag end of this reign, Mahaviracharya flourished and scripted a mammoth and extensive treatise. The name of the Mahaviracharya's book is Ganita Sara Sangraha, or Compendium of the Essence of Mathematics, as it can be translated that way. Daivadnya Vallabha seems to be the first person to write a commentary in Kannada and then in Telugu. A commentary by Varadaraj is also noted by Dr. Pingley. Professor Rao Bahadur M. Rangachari translated GSS. GSS is the short form of Ganita Sara Sangraha in English with extensive footnotes. That is how the Sanskrit text, which was written by Mahavira, comes to in English language, so that one can other world, those who don't know the Sanskrit and only know mathematics through English language, start knowing about the Mahaviracharya's work and contribution. In 1912, this particular work is published by then Madras government. So it is an old story, 1912, nearly 100 years back. Then comes Professor Lakshmikant Jain from Jabalpur, MP. He translated this particular book in Hindi. So for the first time in 1963, it happened there. Ganita Sara Sangraha was translated in Hindi so that other people all over the India should know about mathematician Mahaviracharya and his work and his contributions and his whatever is said in that book. But recently, in 2000 AD, Dr. Ms. Padmavathamma from Mysore critically edited and translated GSS. This work having verse-wise both the English and Kannada translation. So it is a that way I should say a good thing for Kannada people that they have the Kannada authentic Kannada translation of the Ganita Sara Sangraha, and this is published by Siddhanta Kirti Ganthamala, Humbuja Jain Math, district Shumoga, again from Karnataka. And now for this talk, I am referring the same edition by Dr. Padmavathamma. So every time when I referred anything from GSS, it is directly page or verse, whatever I quote, will be from the edition by Dr. Padmavathamma. Now, I have a short account of what are the contents of Ganita Sara Sangraha. This referred edition is subdivided into 9 units or 9 chapters in our language. though the word Sara is appeared in the title, Sara means essence, short form. But this work has whopping 1,131 verses. It seems that Mahavira's definition of Sara is 131 verses. So he might have having some more knowledge, but he has put all his knowledge in 1,031 verses. That is how it appears that his concept of word Sara is there. So whooping 1,131 verses, a lot of things are said at a one stroke in that book, Ganita Sara Sangraha. Of course, this talk is limited to Mahavira's innovative and notable contributions. It is not possible for anybody, of course, to say about all those topics discussed in Ganita Sara Sangraha. So I have selected only 2 topics and some 1 or 2 here or there miscellaneous topics. One topic is Mahavira's contribution in the field of sequences, as discussed in, of course, Ganita Sara Sangraha, and a very notable contribution in intermediate equations or solutions of intermediate equation, along with some miscellaneous topics. So let us begin with what Mahavira has contributed. I repeat the word contributed in the sequences and series. So there are 2 types always, the sequence of natural numbers and sequence in arithmetic progression. Mahavira has given many interesting, less known, and the results which are not even today not in syllabus. So I'm sure many of you may not be knowing what Mahaviracharya has said in 9th century about the results on arithmetic progression as well as sequence of natural numbers. Let us begin with the journey of those results. So first, a very known result, sum of first n natural numbers is n into n plus 1 upon 2. The form which is first given by Sridhara, repeated by Mahaviracharya in a same form in his book. A well-known result, it doesn't need any explanation. Sum of n natural numbers starting from 1. But Indians were keen to develop not only the sum from 1 to n, but from p plus 1 to n. So out of the n natural numbers given 1 to n, first p were left out, and then remaining p plus 1 to n numbers are added. This particular concept is called Shesha Sankalitam, or partial sum of natural numbers. This particular result, Shesha Sankalitam, as given by Sridhara first, repeated by Aryabhata, like this. So if I want to find sum of natural numbers from p plus 1 to n natural numbers, the result is n minus p into n plus 1 plus p upon 2. Same result is repeated by Aryabhata as per the reference given. Shredi Vyavahar Shlok 16 from Sridharacharya and Shlok verse 20 from Ganita Pada of Aryabhata. Same result appears. But what Mahaviracharya has done here, and that is the most interesting thing about his concept of partial sum of natural number, Mahaviracharya extended this concept after discussing the sum of first n terms of AP. Well-known result again, sum of n terms of in arithmetic progression. Again, credit goes to Sridhara, but Sridhara's form is this. The form which we know today, 2a plus n minus 1 into d, is given by Mahaviracharya first in his verse 62, page 16 of the Ganita Sara Sangraha. And this formula, n by 2 into twice a plus n minus 1 into d, is again well known. So credit for giving the formula for sum of first n terms of arithmetic progression as we know today, the form we know today, goes to Mahaviracharya. Of course, he has given 3-4 more forms during the discussion. Now, Mahaviracharya extended what is said about partial sum of natural numbers to partial sum of terms in arithmetic progression. And this is one of the innovative result or the first time in the Indian history of mathematics, such type of result is available. So our sum will be like this, not from T1 to Tn, but sum will be from Tp plus 1 to Tn. First P terms of the arithmetic progressions are ignored, and sum is only taken from P plus 1 at time to Tn. And Mahavira says the result like this. Sum is equal to n minus p upon 2 times twice a plus n plus p minus 1 into d. You will immediately recognize that once I put p equal to 0, means when I take the sum from 1 to n, I will get my usual result n by 2 into twice a plus n minus 1 into d. So this particular extension of taking partial sum of the terms in AP, the credit goes to Mahavira, again in the same chapter called Shredi Vyavhara, verse 107. Let us have one illustration so that we will be able to understand the importance of this. Consider a problem like find the sum from 7th term to 25th term of AP. What we do today for this problem, as we all know, is we first find a sum from 1 to 25, then find sum from 1 to 6, and then subtract. So we will be able to get the sum from 7th term to 25th term. But Mahaviracharya's formula allows us to write the sum directly, or to find the sum directly with A 5 D2 P plus 1 7 N25 and P6. Apply the formula, the sum will be 605. So we need not do 1 to 25 sum, 1 to 6 term, and then subtraction. Directly we can find the sum from 7th term to 25th term of an AP. That is the importance of the Mahavira formula. Unfortunately, this formula, at least whatever I taught or wherever I taught, I don't anywhere this particular formula given, not only given, forget about the name of Mahaviracharya. I have not taught this formula in any of my career. Now, again, a known result, sum of squares of first n terms of numbers, 1 square to n square, 1 square plus 2 square up to n square. Again, a known result, n plus 1 into 2n plus 1 into n upon 6. First given by Aryabhata, repeated by all, including Mahavira. Same result is available everywhere in every text. Now, again, what is the importance of Mahavira? He extended this result to sum of squares of n terms in arithmetic progression. This is again a new thing, not in the syllabus, at least I go through. So what is the idea? To find the sum, not T1 plus T2 up to Tn, but T1 square plus T2 square plus T3 square up to Tn square. Sum of squares of first n terms of AP. Again, with usual notations, A and D. Formula is little bit complicated and long also. But the whatever is given in the verse, formula reads like this. 2n minus 1 into d square by 6 plus a into d multiplied by n minus 1 plus a square, and total addition is again multiplied by number of terms n. This particular formula, when calculated for the given values a, d, and n, gives the sum of squares of n terms of arithmetic progression. This is again a very interesting and innovative contribution by Mahavira. Before, of course, I must say this, before Mahavira, Sridharacharya also has given, but same result, but not in this form. His version was different, but that is a different story again. Now, sum of cubes of n natural numbers is again a known result. 1 cube plus 2 cube plus 3 cube up to n cube. And this is n into n plus 1 upon 2 whole square. Aryabhata was the first again to give this result in his Aryabhatiya. And the same result is then repeated by, without any alteration in the result, by all the scholars. Even today we apply the same result, n into n plus 1 upon 2 whole square for sum of cubes of n natural numbers. What happens for the squares of natural number? Mahavira again extended this result for sum of cubes of n natural number. That is again a very interesting thing. Sum of cubes of first n terms of arithmetic progression. So my sum is now t1 cube plus t2 cube plus t3 cube up to tn cube. Not only t1 plus tn, but it is cube of sum of cubes of first n terms of arithmetic progression. And the result goes like this. Mahavira has given two forms. For a less than d, this form s5 square d minus s5 a into a minus d. And for a greater than d, it is a plus sign. Of course, these two things are not necessary. We can have one result for a any one form for any result. But what is this S5? S5 is sum of n terms of arithmetic progression. So first find t1 plus t2 up to tn, and then substitute that value in any one of the result to have the sum of cubes of first n terms of AP. Again, when a equal to d means it is a sequence of natural number, we will left with S5 squares. So that will be n into n plus 1 upon 2 square. So that way they are all connected. So these two extension from sum of squares of n terms of natural numbers and cubes of n natural numbers to sum of squares of first n terms in arithmetic progression. Similarly, sum of cubes of first n terms of arithmetic progression are the two very interesting and less known results stated by Mahaviracharya in his book. Of course, that verse is 303 on page 402. Now, after discussing such 4 or 5 innovative results, Mahavira stated some identities. These identities are like this. These identities involving powers of natural number n and sums of first n natural numbers are stated by Mahavira like this. So first identity is n square plus n cube plus s1 plus s9. So n square is square of given natural number n. N cube is cube of n. What is s1 and s9 is, s1 is sum of first n natural number, and s9 is sum of sums of first n natural number. Those numbers s1, s2, etc. are given by me just to identify the sums given by Mahavira in the order in the book. So you can have any name for that, but I have just to clarify it. So it is the sum of natural numbers, n natural numbers, plus sum of sums of first n natural numbers. We know the formula. And then added to that, the square and cube of a natural number. This particular identity, according to Mahavira, will give a result as shown. N plus 1 by 2 multiplied by 7n, that bracket minus n divided by 3, and then whole term is multiplied by n plus 1. Of course, we can check the result anytime. The identity is a correct one. Such fashion of providing the identities is not new in Indian mathematics. There are various identities. Sridhara has given 2-3 identities. Then Mahavira has repeated the same. So they were clubbing two sums with numbers to produce a result. Now, natural question is why they require this. And for that, we have to go to the illustrations given by Mahaviracharya or Sridharacharya. Then we will understand what is the necessity or the importance of giving such identities. Now comes another identity. Mahavira termed that identity as Sanghata Sankalitam. What is the definition of that Sanghata Sankalitam? Sankalitam is addition. For natural number n, I have defined them in a language we know well. For the natural number n, the Sanghata Sankalitam, S10 as I marked it, is defined as S1 plus S3 plus S4 plus S9. So 4 sums are added. That's why it is called Sankalitam. So again, S1 is sum of squares of first n natural number. Then S3 is sum of cubes of first n natural number. S4 is, sorry, I have made a mistake. I repeat that. S1 is sum of first n natural number. S3 will be, and S9. Okay, that's all. Cube is repeated twice. So second sum is sum of squares, and the third is sum of cubes of first n natural number. And the sum. So 4 sums which are usually known to everybody. Sum of natural numbers, sum of their squares, sum of their cubes, and sum of sums are clubbed or added to have another sum which is termed as Sanghata Sankalitam. And for that, Mahaviracharya has given this formula. S10 is equal to n plus 3 times n by 4 plus 1 bracket multiplied by n plus n square. It is available in verse 309 at the said page 406. Anybody can check and verify. Now another sum or another identity, similar type of identity which is defined by Mahavira is called Chiti Chitika. I have not translated only because that is a technical term, same as Sanghata Sankalitam. This is a technical term used by Mahavira, so I have not translated to any English or any other language. I kept the same word, Sanghata Sankalitam and Chiti Chitika. What is that Chiti Chitika? The definition is like this: for n terms of arithmetic progression, T1 to Tn, which is a predefined arithmetic progression, this particular sum is summation of 1 plus 2 plus 3 up to Tr. R varies from 1 to n. In simple words, what is done to have a Chiti Chitika or this particular type of sum is, for a given n terms, first I will calculate sum from 1 to T1, that is first term of the given AB. Then 1 to T2, 1 to T3. This cycle I will continue up to 1 to Tn. So for a given n terms of arithmetic progression, we need to calculate n sums starting from 1 to Tr. That's why it is said sigma 1 to Tr. And then all those sums are added. All those n sums are added. Whatever we get is named by Mahaviracharya as Chiti Chitika. Again, this result is not available in our syllabus. Let us have an explanation. Consider a arithmetic progression 4, 7, 10, 13. So I will calculate sum 1 to 4, 1 to 7, 1 to 10, 1 to 13. 4 terms are only I have selected. And then I will add all those 4 terms. So my Chiti Chitika will look like this: 1 to 4, 1 to 7, plus 1 to 10, plus 1 to 13. Of course, answer is 184. That can be actually calculated. And then Mahavira has not only defined the sum, but given a formula for this Chiti Chitika. And that formula reads like this. Again, a very complicated looking form, but I cannot do anything because whatever Mahavira has said is this. The translation of the verse comes to this, or decipheration of that verse gives this much result. Twice n minus 1 upon d into d square by 6 plus d by 2 into a into d. It looks complicated, definitely. Times n minus 1 plus a into a plus 1, and then holds that sum is multiplied by n by 2. This is again very important, not much complicated, but it is difficult to remember. But after practice, good practice, we will be able to remember the formula for Sanghata Sankalitam as well as for Chiti Chitika. Now the last in the run. The term Adhikahina Guna Sankalitam is used by Mahavira. Again, I am not going to translate that. Adhikahina Guna Sankalitam. Guna Sankalitam is geometric progression. So this particular sum, Adhikahina Guna Sankalitam, is a combined sum of terms in geometric and arithmetic progression. Not in the exact sense of what we call today geometric sequence, not that way. It is again something different. Let us define what Mahavira is saying about his Adhikahina Guna Sankalitam. So for rational set of positive rational numbers from A, R, and M, and n natural numbers, the terms of Mahavira's series are defined like this. This is how he is saying. The first term is a second term. I have purposely given dash to that to differentiate between the terms of arithmetic progression and terms of Adhikahina Guna Sankalitam. Second term will be R multiplied by first term, that is T dash R, T dash 1 R plus or minus M. So we multiply by R first and then add M. That is how the next term will be there. T dash 3 will be T dash 2 R plus or minus M. Both are accepted, plus M and minus M. And terms goes up to nth term T dash n is equal to T dash n minus 1 multiplied by R plus or minus M. So every term after first term is obtained by multiplying by R to previous term, and M is either added or subtracted. This is how the terms of the series are formed. Of course, when it is a case of Sankalitam, all these n terms now, T dash 1 to T dash n are added. A is the first term, R is the standard multiplier, and M is the common additive. So what happens? What Mahavira said, I have amended this result slightly. In one of my research papers on this Mahavira's series, and in particular this Adhikahina Guna Sankalitam, I first define, which is not done by Mahavira, what will be the nth term of Adhikahina Guna Sankalitam, without which one cannot prove the Mahavira's result. So the amended results are as follows. The first result, first sum, when R is greater than 1. Of course, we know there are 2-3 cases when there is a question of geometric progression. R greater than 1, Adhikahina Guna Sankalita, which I have denoted by S dash N, that sum, particular sum, will have this complicated formula again. It will be plus or minus M divided by R minus 1 multiplied by mod of R raised to N minus 1 upon R minus 1 minus N, added by plus A times R raised to N minus 1 upon R minus 1. You will realize that the second term is the sum of geometric progression when R greater than 1. A times R raised to N minus 1 upon R minus 1. So this will be the answer for Mahavira's Adhikahina Guna Sankalita. And this result is stated by Mahavira. I have just translated that result. But other two, absolute value part is added just to ensure that whatever difference we get should be plus sign. That is what is said by Mahavira. That's why that absolute sign is added in the formula. This result is whatever you are seeing on the screen. The same result is stated by Mahavira in the script. But this is for extended for R less than 1 like this. M into R minus 1. But now it will be 1 minus R raised to N upon 1 minus R. And geometric sum will be added A times 1 minus R raised to N upon 1 minus R. And when R is equal to 1, that will reduce to simple result of N by 2 times twice A plus or minus N minus 1 into M, where M will stand for D for R equal to 1. So this is how Mahaviracharya has defined Adhikahina Guna Sankalitam. As I said in one of my research papers, I have discussed all these sums, including their Sanghata Sankalitam, and every sum of squares of n terms, sum of cubes of n terms, then Sanghata Sankalitam, then all the results in details. And not only discuss, I have furnished the inductive proof of each of the result. So to my satisfaction, only for my side or anybody's very sad, you might be having a thought where is the proof, whether all these results are correct or not, where is the justification, what is the rationale, where there is any rationale for all these results, whether can we prove these results. Answer is yes. We can have an algebraic interpretation, algebraic rationale for each of the results stated by Mahavira. Not only that, every result can be proved by using first principle of mathematical induction, which I have done for my satisfaction. So I can confidently say that after having the proof with me that all the results are correct. Of course, there was no doubt in my mind that Mahaviracharya might have made some mistake in giving those results, first just to satisfy the query of a mathematician, where is the proof, whether the proof exists or not. Because and I am very sure that Mahaviracharya must have been having the proof, only because a scholar of the stature of Mahaviracharya will not say anything without proof. But the script is written in Sanskrit, that too in a verse form. So there is a practice of giving only results without any proof, without any justification, without any rationale. All those things of explaining them, giving a justification, giving a rationale, giving a proof are left to either to the commentator or to the teacher who actually teaches those subjects in the classroom. That was the style of writing Indian scripts. That was the, you open any book, you open Lilavati, you will get only results. You open Aryabhatta, you will get only results. No justification. All things were done later by either by commentator or by various scholars at various stages. Now, lastly, before I close my topic, I move to two miscellaneous results, as I am calling them. Just I have selected from a topic. The first result is from Kuttaka, as it is called. Solution of tangent pulverizer in today's term. But the Indian name is Kuttaka. What is this Kuttaka? Kuttaka is a linear indeterminate equation. And what is linear indeterminate equation? Linear indeterminate equations are the equations where number of variables in the equation are greater than number of equations available. Means a simple equation like solve 3x plus 4y equal to 7, or solve 5x minus 3 is equal to 9y. There are two variables, x and y, but available equations is only one, 5x minus 3 equal to 9y, like that. So such equations are called indeterminate equations, first degree indeterminate equations, or linear indeterminate equation. In Indian part of the story, these equations are, in Western, they are called Diophantine equation. In India, well before Diophantine, the name Kuttaka was given to such type of equation by Brahmagupta, and lots of attempts were made by starting from first Aryabhatta to Bhaskaracharya to Narayan Pandit and so many. So nearly 1000 years, these solutions were tackled. For various methods, various suggestions were formed. But why that much effort? Only because Indians are expecting the solutions of such equations in integers. For rational solutions, the part is simple. But to find an integer solution for ax plus c is equal to by, abc, any integer plus or minus, it's really a difficult part. Indians have attempted a lot. In that series, one important stage is the contribution of Mahavira. I must admit that Aryabhatta 1 was the first to initiate the study, later carried out by many. After Mahavira also, Bhaskaracharya has done a lot of work on the issue, but Mahaviracharya is one of the important stage of those attempts in giving the solution. And in Ganita Sara Sangraha, he has discussed nearly 6-7 types of Kuttaka. And the word Kuttikara is used by Valli Kuttikara, Samakuttikara, etc. in Ganita Sara Sangraha. A whole lot of pages, nearly 300 pages, 200-300 pages were devoted for this chapter, particular chapter, for verses, so not pages, not verses. Total verses were devoted by Mahaviracharya. But during this attempt, Mahaviracharya has exactly contributed for the first time is solution of conjunct pulverizer, or means the system to solve a system of equation in integers like this. In today's words, just Forget about those kuttaka and kshepa and all those words, bhajya, har, etc. Just have a known language. The system of equation before me is a1x plus c1 is equal to b1 y1, a2x plus c2 equal to b2 y2, and equations like that. An attempt is made to solve these n equations simultaneously for x. And of course, then y1, y2 can be derived from that. So what was the aim? Aim is to solve n equations of this type, a1x plus c1 equal to b1 y1, in integers. Mahaviracharya was the first to give the answer for this problem, solving n in linear indeterminate equations simultaneously. So it is a problem of simultaneous indeterminate equations attempted successfully by Mahavira for the first time in history of Indian mathematics. And this is a very notable Indian contribution. Which type of problems, again, the same question, which type of problems are dealt? What was the purpose of doing this? I will give you one example. I have just restrained myself to quote any verse, but now I am quoting the verse from Mahavira, this verse. Again in Sanskrit, no doubt, but those who know Sanskrit will understand that this is a distribution problem. Vanantare dadimarashayaste panthaistraya saptabhirekasheshaha saptastrishesha navabhir vibhaktaha panchashtabhihi ke ganakat viragraha. It is available in chapter 6, verse 28. What is the translation of the problem in the verse? The translation is like this. In the interior of the forest, 3 heaps of pomegranates were equally divided amongst 7 travelers, leaving 1 fruit as a remainder. Similarly, 7 heaps were divided among 9, leaving 3 fruits, and 5 heaps were divided among 8, leaving 2 fruits. O mathematician, what is the number? Means what is number of fruits per heap? I will not explain how what is that. Vanantare means in the interior of the forest, etc. Believe me that the translation given in the book, I have simplified that translation so that we can understand. This is a modern distribution problem, as we used to call it today. That some hips were there and they are distributed amongst the travelers or amongst the recipients in some proportions. Mahavira solved his problem successfully, of course. So answer in the system which we need to solve is this. From the data given, we have equations 3x minus 1 equal to 7y1, 7x minus 3 equal to 9y2, and 5x minus 2 equal to 8y3. And the answer given or answer obtained is 138 fruits per heap. I suggest all of you to try this somehow, somewhere by Mahaviracharya's method, and then we will enjoy the beauty of the situation and contribution of the Mahavira in that field. Of course, I'm not going into details of the answer of the problem or the how the equations are solved. That will take a lot of time for us. Now we come to the last one, Mahavira's formula for NCR. Mahavira tackled a problem on permutations and combinations. The Sanskrit word or Indian word for such is Ankapasha. Formula is or Prastara Veda Yoga, the term used by Mahaviracharya. But again, in the history of mathematics, Mahaviracharya is the first scholar to state the formula for number of combinations under the caption Prastara Yoga Veda. Again, I have translated that formula in known notation. NCR is equal to number of combinations of n things selected are at a time. Mahavira's version is like this. Numerator n into n minus 1 into n minus 2 up to n minus r plus 1 divided by 1 into 3 into 4 into up to r, means factorial r in our language. But this formula, when I compare with Aragon's formula, remember Aragon appears in 1634 and this known result is this. NCR is equal to factorial n upon factorial r into n minus r. Nearly 800 years difference, that's a historical part of the story. But the format of the formula or the version of the formula when I solve both any result by Mahavira formula and this formula which we used to apply in our syllabus, I found that this particular, of course, they are equivalent because factorial n divided by factorial r, factorial n divided by factorial n minus r will leave me n into n minus 1, that numerator. That's the correct way. But the formula given by Mahavira is easy to apply than the formula by Harrigan. Just it's a matter of comparison. I'm not going to take any credit from Harrigan about this. Only historical sequences that way. So with this, Mahavira has given why he has written the book. What was the purpose, or what was the thought process, or what is his idea about mathematics? In the very first chapter, he has given some 6 to 7 verses under the title Ganita Prashansa. So he's praising mathematics. And what he is saying about it, that he enlisted the Shastras where Ganita is mandatory. So without Ganita, you cannot do anything in these Shastras. That list includes all worldly affairs, Vedic and Laukik, as he is saying. Then in science of law, in wealth, in music, in drama, in cooking, in medicine, in architecture, proceeding, poetry, logic, grammar, a lot of things, whatever I said, in the space available with me. Many more Shastras were quoted by Mahaviracharya, where mathematics is not only useful but mandatory. Without mathematics, you cannot work properly in all these fields. You will be handicapped without mathematics. So what he is actually saying in the verse, after quoting all these Shastras where mathematics is mandatory, he says, Bahubir vipralapaihi kim trailokye sacharachare yat kinchit vastu tat sarvam ganitena vina nahi. So after quoting lot Shastras, he said, or kya bolna, what to say more? Bahubir vipralapaihi kim. In all the total world, whatever is there cannot exist without mathematics. This is the thought process, or this a representative thought process, I must say, of all the Indian scholars to mathematics, that yat kinchit vastu tat sarvam ganitena vina nahi. And with this attitude, with this thought process, they developed mathematics useful to human life. With these words, I end my lecture. I once again thank you all, particularly Honorable Vice Chancellor and authorities of the university, authorities of the Department of Mathematics, convener of the program, all the participants, which I am seeing on the screen, more than 150 participants. I hope that you might have enjoyed my lecture. Whatever I can say in short time, I tried to say this thing. As I said at the outset, that I'm daring because I should not say many things about Mahaviracharya because he hails from Karnataka and on the platform of the university, Kannada University. But once again, Namo Namaha. Thanks for all. Thank you very much.
Thank you. Thank you, sir. Thank you very much. Myself, Dr. Sandeep, sir, Assistant Professor of Mathematics, contacted you multiple times. Sir, am I audible to you?
Yes.
Yeah. Sir, thank you very much, sir, for your wonderful talk. And we are happy to know that Mahaviracharya from Karnataka, just now we came to know through your talk. Previously, we don't have any idea on that. And in addition to that, you have given awareness on Mahaviracharya contributions on sequences and series and linear indeterminate equations and the Mahaviracharya formula for the combinations and many more other concepts. And thank you, sir. Thank you very much for your wonderful talk. We are very much benefited through your talk. And thank you for your valuable time preparing for us, for accepting our invitation. Thank you, sir. Thank you.
Thank you very much. Allow
Okay,
me
sir.
to leave.
Thank you. Thank you, sir. Thank you very much. Yes, sir. Thank you. Sure. Thank you, sir.
Dear participants, stay tuned till our next speaker joins us. A very warm good afternoon to everyone. I would like to know Professor K.C. Prasad sir is here with us. Sir, kindly confirm your presence here. Yes, sir is here with us. Sir, am I audible to you?
Yes, yes, yes. No, sir.
Okay. Okay, sir.
Yes.
So, I, Megha Khandelwal from Department of Mathematics, feel immensely pleased to have with us Professor K.C. Prasad, retired professor from Ranchi University, Ranchi. Sir is going to give a talk on mathematical contributions of India before 1200 AD. So, sir's main research interests have been theory of numbers, specifically
Right.
Diophantine approximation.
Diophantine approximation. Main stream of work is Diophantine approximation of irrational numbers. Lagrangian Markov spectrum, etc.
Yes, as sir is confirming, his research area has been theory of numbers.
Yeah. Yeah.
So I am here to give a brief introduction of Professor K.C. Prasad and welcome him.
Thank you. So may I now start?
Yes, sir, you are audible.
May I now start?
So,
yes, sir. Oh, yes. My topic is, am I audible? Am I audible?
sir, I would like to give you an introduction to our participants.
क्लियर नहीं आ रहा है आवाज.
Just 5 minutes of time to give you an introduction, and then it's all over to you.
Yes, yes. You are audible, sir. Now. Well,
sir, I would ask your permission for giving your introduction to the participants. Am I audible to you,
yeah,
sir?
I am audible. You are audible?
Yes, sir. Please allow me to give your introduction to the participants present here.
Right. Go ahead.
Okay. Okay, sir. So, as sir himself told, that his research interests are theory of numbers, specifically Diophantine approximations and combinatorics.
Right.
That's in designs and Hadamard matrices and sequences
Right.
Sir completed his early education from Dumka, and after that, he completed his PhD in 1977.
Right.
He started his career with being a lecturer in Ranchi College, and then he joined Ranchi University as a reader in 1980.
80, right?
In the year 1985, Sir became a full professor of mathematics in School of Sciences of Ranchi University. Sir
Right.
had been at various administrative capacities in his career. A few of them to mention here are Director of UGC Academic Staff College
Staff College
from
also.
2002 to 2006. He retired in 2000 School of Sciences in Ranchi University. Sir also had been visiting professor in Central University of Jharkhand and Jharkhand Raksha Shakti University. Sir has more than 45 years experience in teaching master's and degree courses of mathematics.
And also
And
in Central University.
Yes, right, sir.
Right.
Yes, sir has also worked as a visiting professor in Jharkhand Central University. And sir's work in promotion of research has been impeccable. Sir has written 23 research publications, and most of them are listed in SCI or WAS database. Sir has edited 13 volumes of Mathematical Journal of Ranchi University. Also, he published a book on matrices and linear algebra. Many of us refer that to. And Sir has conducted UGC major project and Diophantine approximation associated with Markov like chain. Sir had been resource person of National Board of Higher Mathematics for evaluation of research projects and appointments of research fellows for Mathematical Institution of Jharkhand. Sir's major research work focuses on Diophantine approximation and combinatorics, and presently he is working to find a relation between constant of infinity of approximations and the constant for one approximation of Markov theorems. Sir has done great efforts which have been successful for popularization of mathematics in Jharkhand and India, such as working as regional coordinator for atomic energy, Government of India from 1999 till now. Sir started celebration of Ramanujan's Day and Maths Festival, etc. in University of Ranchi and also some other colleges of the area such as St. Xavier College, VIT Mesra, and many other colleges. Sir also started biannual conference on mathematics in Ranchi University. He has been doing many services at administrative positions and mathematical field in via different modes. Sir had been General Secretary of Jharkhand Society of Mathematical Sciences from of Journal Mathematical Reviews of American Mathematical Reviews, a journal in American Mathematical Society. Also, Sir has been president of Jharkhand State Unit of Vigyan Bharati from 2009 to 2012. Sir has also been convener of IMS Symposium on Continued Fractions in 76th Conference of Indian Mathematical Society, and also has presented talks at various international conferences. And this list continues. We are highly inspired to see you, like from the very young age till now, you are constantly inspiring and doing work in mathematics, and still you are actively participating in mathematical research, sir. So we all are all ears to hear you. So I welcome you to this today's seminar on the eve of National Mathematics Day. And Sir is going to give a talk on mathematical contributions of India before 1200 AD. Welcome to you, sir.
Before 1200 BC, not AD. Mathematics in India before
1200 BC.
Before 1200 BC. Okay.
Okay, I'll make a correction, sir. It's 1200 BC. All years here to me.
Yeah. This I had informed earlier that the topic is going to be mathematics in India before 1200 BC. So, should I start now?
Yes.
Yeah.
Huh.
Am I audible? BCAD को confused.
Yes, sir, you are audible.
Okay. The topic demands a narration of historical perspective. Experts opine no subject loses more than mathematics when dissociated from history. There has been a numerous demand to make mathematics easy to read. We teachers are anonymous that if a topic is introduced in the classroom with the narration of its historical development, that is course of development, understanding mathematics becomes easy. Now, NCERT is also writing texts on this idea. Well, on the basis of historical and archaeological conclusions, the Indian subcontinent is one of the world's oldest civilizations with pre-Vedic history. Interestingly, Vedic hymns are estimated to be of around 20 lakhs BC, before Christ. In Yajurveda, a verse goes as follows: Yatha Shikha Mayuranam, Naganam Manayo Yatha, Tadvara Vedanga Shastranam, Ganitam Murdhani Sthidam. This means, as are the crests on the heads of peacocks, as are the gems on the hoods of cobras, so is mathematics at the top of all sciences. In this verse, we find the reference of cobras, scientists, and mathematicians. Doesn't it indicate that these objects, peacock, cobra, and mathematicians, must have existed long before writing of this verse? So we conclude that the stream of mathematics in India is present since pre-Vedic days. In fact, Indian civilization is a creation of the spiritual leaders of this land. Even today, none else in India.
Excuse me, Professor K.C. Prasad, sir.
Yes.
Excuse me, Professor K.C. Prasad, sir.
Yeah.
Sir. Professor K.C. Prasad, sir.
Yes, I am hearing.
Yes, sir. Are you sharing the PPT? Otherwise, just giving talk. Are you sharing, sir, any PPT?
No, PPT कोई PPT बना हुआ है, मतलब कोई PPT presentation है.
No.
I will.
Okay, fine.
I will send up.
Thank you. Sir.
Well, if required,
Thank you, sir.
I will
Not
take
required, sir.
a day or
It's not
two.
required, sir. You can,
I see.
sure, sir. You can,
So should I continue? Okay, should I continue?
Yes, sir. You can proceed, sir.
Sure.
Yes, sir. You can
So
continue.
I was saying that
Professor Prasad, sir, you can continue.
I was saying that Indian civilization is a creation of the spiritual leaders of rishis of this land. Even today, in India, a Mahatma or a saint or a sage receives highest order of honor, we
रिकॉर्डिंग हो रहा है, बोलिए सर।
I see. Thank you. We witness even now that PMs and presidents of India frequently pay visits to Devaraha Baba, Ogareshwar, Pirate Baba, etc. Life of our Adi Shankaracharya is obviously miraculous. He died at an early age of 30, but moved across every part of the country and established spiritual chairs of Shankaracharya in Rameshwaram, extreme south, Jagannath Puri, extreme east, Badrinath, extreme north, and Dwarikadhish, extreme west. In fact, Adi Shankaracharya was particular to guarding our spiritual heritage from all the four sides by establishing vibrant spiritual pillars like Shankaracharya's of these four peaks. Einstein compliments, we owe a lot to Indians who taught how to count, without which no worthwhile scientific discovery would have been possible. The German mathematician Kronecker of the 19th century said, God created natural numbers and all the rest of numbers are created by man. Counting is a very primary requirement of a man since the inception of civilization, and evolution of this process of counting has taken centuries to appear in the present form. And present expression of decimal system, which requires a peculiar number 0. 0 is worldwide acknowledged as a most wonderful gift of India to the globe. To Indians, it is a divine gift of our anonymous inspired rishis. Swami Ramatirth, an Indian philosopher and a yogi, was once invited to Japan. He delivered a lecture there on 0. Swami took 3 days to finish his lectures. In Durga Saptashati, there is a prayer, Atha Tantroktam Devi Suktam. Here it is said that words appear first, and then consciousness, and then intellect, etc. And finally, our gross manifestation. So, to understand the mysteries of creation, one, Jivatma, requires to transcend the realms of intellect and consciousness and stay in the subsequent realm of intuitions in its upward journey. As a researcher of mathematics knows it better that every good piece of his or her research is necessarily backed by some flash that he receives in course of his or her deep reading and thinking. This flash is a mysterious object, and in fact emerges from the divine realm of nature, This realm of nature this realm is the realm of intuition. This is how knowledge of mathematics is growing everywhere. So in India, mathematics is taken as an inspired human creation. In general, people describe it as human creation, but we call it an inspired human creation. In fact, Aryabhatta, a mathematician and an astronomer of Patliputra school, which flourished in Maurya Empire, was first to systematically collect and write a book, Aryabhatiam, of all known components of mathematics and astronomy till date. He systematically introduced decimal system of Vedic origin and related mathematics of their addition, subtraction, multiplication, and division in decimal form. Aryabhatiam is divided into 3 sections: Ganit, Kalaganana, that is time calculation, and a sphere. In Ganit, Aryabhatta records up-to-date knowledge of numbers, decimal system, and arithmetic of natural numbers, and gives algorithm for obtaining squares and cube roots in decimal form. His one meticulous observation related with geometrical measurement, e.g., a ratio of circumference by diameter of a circle is 62,832 upon 20,000 equal to 3.1416 dot dot. He observed it as a constant called pi. He also found the length of equator of Earth as 24,895 miles, 0.2% smaller than our present estimate, 29,902 miles. He was brilliant. He did a lot of geometry. To summarize, geometry proper was invented during the origin of Vedic rituals, while its approximation and further development was done by Greeks also. I would like to come to algebra, the very pillar of modern civilization. Let me tell that the sine and cosine functions are the backbone of modern trigonometry. Recall that all periodic functions, in fact, most functions, are expressible as possibly infinite linear combinations of sine and cosine functions. Well, invention of algebra has been attributed to Bhaskaracharya, to the ancient sages, our ancient sages. No, sorry. Invention of algebra has been attributed by Bhaskaracharya to our ancient sages. The genesis of the algebraic character of Indian mathematics can be traced to impact of Panini Ashtadhyaya of 14th century BC. By the time of Brahmagupta, 628 AD, the subject of algebra had evolved in India into a distinct branch of mathematics and became one of the central pillars. After evolution through several stages, algebra has now come to play a key role in modern mathematics. It is remarkable how early the Indians realized the significance of algebra and how strongly the leading Indian mathematicians like Brahmagupta, 628 AD, and Bhaskara, 1150 AD, asserted and established the importance of algebra. Brahmagupta, described as an algebraist acharya, among the once remarked, as the sun eclipses the stars by his brilliance, so the man of knowledge of algebra will eclipse the fame of others in assembly of people, and still more if he solves some algebraic problems. He referred to algebra as Kuttaka, as Kuttaka. That's it is a science of solving problems by a process of simplification, by breaking quantities into smaller and smaller pieces. Later, mathematicians like Bhaskara too used a current Sanskrit term Bijaganit. Bij means seed or root. Algebra is a science expressed by symbols, requiring keen and clear intelligence, analysis, ingenuity, sagacity, and wide imagination. Another momentous step in the development of mathematics was taken by Indians when they enlarged the number system by introducing negative numbers. Brahmagupta, 628 AD, gave the rules for algebraic operations involving zero and negative numbers. He brought out the difference between positive and negative numbers by attaching to them the ideas of possession and debt, respectively. The Indians have been comfortable with irrational numbers right from Vedic ages. Bhaskara too gave a beautiful identity. Difficult to write or describe here. It is used for computing the square root of binomial surds. Of course, it adds convenience in computation. It is about under root A plus minus under root B. Thanks to the early recognition of the existence of negative numbers, the Indians would give a unified treatment of the various forms of quadratic equations with positive coefficients, that is ax squared plus bx plus c, ax squared plus c is equal to bx, bx plus c is equal to x squared, etc. The Indians were the first to recognize that a quadratic equation has two roots. Sridharacharya 750 AD gave the well-known method of solving a quadratic equation by completing a square method. An idea which later received far-reaching consequences. Ancient Indians knew several useful results on permutation and combination, including the formula for NPR and NCR. The Pascal triangle for quick computation of NCR is described by Harayudha in 10th century AD as Meru plus 700 years before it was stated by Pascal. A famous text on history of mathematics the American historian C. Kajori, 1859 to 1930, concludes, it is remarkable. His quote I am reading. It is remarkable to what extent Indian mathematics enters into the science of our time. Both the form and the spirit of the arithmetical algebra of modern times are essentially Indian. Thanks for our notation of numbers brought to perfection by Hindus. Think of the Indian arithmetical operations nearly as perfect as our own. Think of their elegant algebraic methods and then judge whether the Brahmins of the banks of Ganges are not entitled to some credit. The climax of Indian achievements in algebra was the development of an astonishingly brilliant algorithm for finding all integer solutions of the equation x squared minus dy squared equal to 1, where d is a positive integer. The problem has important application in modern number theory. for D is equal to 61, a case explicitly mentioned by Bhaskara too. The smallest positive integral solution is X is the number 17663190049 and Y is the number 226156980. Look at the unexpected intricacy of the problem. As early as 624 AD, Brahmagupta gave a partial solution of the problem of solving x square minus dy square equal to 1 in integers. Let me remind you that he also created negative numbers. Negative integers were not known before. He showed how to generate infinitely many distinct integer solutions from a given non-trivial integer solution of x square minus dy square equal to 1. And moreover, he showed how to construct one solution of the equation x square minus dy square equal to 1, where m is -1 or +-2 or +-4. This already enabled him to give infinitely many solutions in a wide variety of difficult cases, like D is equal to 83 or D is equal to 92. The critical step in Brahmagupta's partial solution was the lemma. If P square minus DQ square equal to M and R square minus DS square equal to N, then PR plus minus DQS square minus D times PS plus minus RQ square equal to M into N. This lemma was rediscovered by great Swiss mathematician L. Euler in 1764 AD. Of course, using this lemma, Brahmagupta defined a multiplicative structure of the set of all integral equations, the solutions of this of this equation, d square minus p square minus dq square equal to 1. If pqm denotes a triple of integers satisfying p square minus dq square equal to m, then Brahmagupta defined a law of composition called samsambhavana. PQ semicolon M into RS semicolon N is equal to PR plus DQS, comma, PS plus QR semicolon M into N. This is the first instance of an involved group theoretic thinking in mathematics. Brahmagupta anticipated it nearly 1200 years ago. The modern mathematics where modern mathematics of associating an abstract structure on solution set of an equation is found. In order to solve this equation, the original ideas involved in his samsambhavana, along with his numerous other outstanding results, at an incredibly early date, 628 AD, marks him as one of the greatest algebraists in the history of mathematics, with whom none else than Galois can be matched. Hindus believe that is simply a change of cloth. That is change of body form. So, it not be an exaggeration to believe of course, I believe that Galway is next manifestation of Brahmagupta encapsulated in human body. It is amazing that a person, Brahmagupta, who had to introduce negative numbers and its operations in mathematics, who even had to work at basics like developing symbolic algebra, could take a leap into the partial solution of hard problems of determining integral solutions of x square minus dy square equal to 1, introducing group theoretic ideas in the process. All this was achieved by the age of 30. One has only to compare the time taken by Europe to understand or rediscover this idea. While negative numbers began to be accepted in Europe around in 16th century, Eiler rediscovered Brahmagupta's Samasambhavana principle in the 18th century. Brahmagupta really deserves the title Ganak Chakra Churamani. Ganak Chakra Churamani. Jewel among the mathematicians. Churamani means jewel. Jewel among the mathematicians. That another great algebraist, Bhaskaracharya, gave him more than 500 years later. Nowhere in the history of mathematics, prior to 17th century, can one find an algebraic work of comparable depth, ingenuity, and complexity as Chakravala algorithm. The German mathematician Henkel has exclaimed in 1874, the Chakravala is beyond all praise. It is certainly the finest thing achieved in the history of numbers before Lagrange. Bhaskara used this skill and ingenuity to solve several other equations by transforming them to an equation of that type, x square plus minus dy square equal to 1, x square minus dy square equal to 1. And divide solutions to several number theoretic problems. Indian works in this era of mathematics were too far ahead of the times to be noticed by contemporary and subsequent civilizations, with the result that they didn't reach Europe during its renaissance. See, Kazori laments, unfortunately, some of the most brilliant results in indeterminate analysis found in Hindu works reached Europe too late to exert the influence they would have exerted had they come 2 or 3 centuries earlier. Several centuries after the Indian Chakrawala algorithm, Fermat raised the problem of finding integer solutions of x square minus dy square equal to 1. Regarding this question, and revised in 1984, remarks, what would have been Fermat's astonishment if some missionary just back from India had told him that his problem had been successfully tackled by mathematicians almost 6 centuries earlier. The problem was solved in Europe, first by Brouncker and later by Euler and Lagrange, using theory of simple continued fraction. So some sambhavana is in fact easily takes one to the algorithm of simple continued fractions.
आप लास्ट कर सकते हैं सर, लास्ट कर सकते हैं बोल के।
कितना हो गया समय?
50
हाँ?
50 लास्ट कर सकते हैं, पीडीएफ पे भेज दीजिएगा, लेक्चर कर दीजिए।
Well, the common question as to how mathematics is useful in our common worldly life is also well addressed in India through Sulva Sutras. I would like to mention a line in this regard at the end. Sulva Sutra deals with the geometry of different fire altars. We call them Yagya Kunda, which have different shapes and are used to invoke supports of different deities who are in charge of different resources required to make a man happy. So this is in India, mathematics is blended to address the daily life problems of the Indians, I should say, through Sulva Sutras. So this is my last comment. I feel time is up. Okay?
Yes, sir.
Am I audible?
Yes, sir. You have been clearly audible throughout. Am I audible to you, sir?
So after describing use of mathematics in day-to-day Indian life to make life easy through Sulva Sutras, through Yagya Kunds, I would like to finish my delivery. Okay?
Yes, sir. You have been clearly audible throughout this session, and we are extremely privileged that we heard you for an hour, and you iterated very beautifully that how years, thousands of years ago, even then mathematics was considered as the queen of sciences, as equal to the feather on peacock's head in Indian ancient scriptures. And from there you begin the like how the value of pi has been approximated years before the Western mathematicians did, and even the contributions of Bhaskaracharya, Brahmagupta, and their findings of existence of negative integers and quadratic equation solutions. So what your lecture has been highly knowledgeable, and it took us to the galore of ancient historical mathematics. Thank you so much for your wonderful presentation and lecture, sir. We want to thank you a lot from the Department of Mathematics.
Thank you. Thank you very much.
Thank you so much, sir. I request the participant to stay tuned for the next lecture, which begins at 4 p.m.
You told, you told, na?
I told them to stay. I didn't welcome or anything to come and say. Nothing I said. Yeah.
Seniors. Fine. Just I think. Fine, fine. I will take right. Sir, Kanan sir, am I able to you?
Yes, yes, I'm listening to you.
Yeah, thank you, sir. Good evening, sir. How are you, sir?
Good evening. Yes.
Sir.
Yes, now I'm ready.
Okay, fine, sir. How are you, sir?
Fine, fine.
Good, sir. Good.
Glad to meet you.
Thank you, sir. After a long time, I'm seeing you, sir.
Thank you.
Yeah. We'll start the session, sir.
Just give me a couple of minutes.
Respected, today, invited speaker, Professor V. Kanan, sir, and other delegates. Welcome you all to the today's invited talk. Can I go ahead, sir?
Did I miss anything?
No, sir. If you permit, then we'll proceed, sir. Sir,
Please,
permit, then we'll proceed, sir.
please
further.
proceed, but your voice is breaking. Let us see. Proceed.
No, if breaking, sir.
Hello?
Fine, sir. Fine, sir. Respected today invited speaker, Professor V. Kanan, sir, other delegate members, invited talk on international seminar on. I would like to introduce today invited speaker, Professor V. Kanan, sir. Sir currently is working in the SRM University, Amravati, Andhra Pradesh. Sir is retired professor from Department of Mathematics Statistics, University of Hyderabad. Sir did a bachelor degree, BSc and MSc from University of Madras, as well as Sir completed MPhil PhD from Madurai University. Sir started teaching career in Madurai University as a lecturer. After that, Sir joined University of Hyderabad as a reader. After that, Sir becomes the full professor in 1985. After that, Sir was retired in 2016. Sir has, I think, University of Hyderabad, I think, Sir taken various administrative level works. That is, namely, I can say that Sir worked as a Dean School of Mathematics and Computer Science 2002-2005. After that, Sir worked as a Pro Vice Chancellor of University of Hyderabad in 2006 to 2011. Mostly, Sir used to work in the research area, Sir. Links between the topology and category theory and topology dynamics, chaos theory, and ordinal invariants in topology. Sir has several awards and fellowships. Few of them I will name it. Sir received a fellow of Andhra Pradesh Academy of Sciences, Totadri Iyengar Award for Excellence in Mathematics from Chennai, Gnana Nidhi from the Academy of Sanskrit Research, Mullikante from Karnataka State. Sir received Fellow of Indian Academy of Sciences from Bangalore. Sir received Fellow of Indian National Science Academy from New Delhi. Sir received, Sir was acted as a president of Indian Mathematical Society. Later, Sir also becomes national lecturer, award received from the UEC. Sir received ISCA Srinivas Ramanjan Award from Prime Minister of India. Sir also received Fellow of National Academy of Sciences, Allahabad. Sir also received a doctorate literate in the Vachaspati from Rashtriya Sanskrit Vidyapith Tirupati. Again, Sir also received Vidran Mani from Hayagriva Vidyapetam from Chennai. Sir published more than 100 research articles in mathematics in various prestigious journals. Sir also edited several books in mathematics like fractal, wavelets, and geometry, etc. Sir also editor of several magazines and journals other than the mathematics like Sanskrit, Tamil, and English. With these few notes, I think if you go Sir achievements, and we have several achievements are there. I'm quoting you a few of them only. With this, the brief introduction, I would like to welcome Professor V. Kannan Sir to two-day international seminar on Indian mathematician and their contribution. With that thing, I'm handing the session to you, sir. You kindly take over the session, sir.
Thank you. Thank you, Dr. Ballam Srinivasulu. I'm happy to be a part of this two-day international conference on Indian mathematicians and their contributions. I'm happy to find that more than 100, much more than that, participants are listening to this in the Zoom platform itself. There may be more there directly participating. I'm happy to be with you today. I have visited Karnataka, Gulbarga several times, but this may be the first time that I'm visiting Central University of Karnataka. Let me start by a brief summary of what I'm going to say today. I have selected just two formulas which are related to each other. Both of them are on permutations and combinations, and I'm going to discuss the history of those two formulas. History means in which century were those formulas discovered, by whom, and what is its importance. Now I'm sharing my screen. I'm waiting for a while to allow you to see the screen. Are you able to see the screen?
Yes, sir. Yes,
okay. Sir. Okay, then I will go ahead. We know the notation N choose R for the number of ways of choosing R objects from N objects. These are also called binomial coefficients because in the binomial expansion of A plus B whole power N, these coefficients N choose R, these numbers are arising there as coefficients. That's the reason that they are called binomial coefficients. Regarding these numbers, there are some very elementary natural formulas, and today we are going to take up just 2 of them and then discuss who discovered it first. The first formula is the well-known one which we introduced at the junior college level. All our students learn it. Formula for N choose R, it is factorial N divided by factorial R into factorial N minus R. The second formula is known by the name of Pascal's identity. It states that N plus 1 choose R is same as N choose R plus N choose R minus 1. These are the 2 formulas whose story, whose history we are going to see today. I'm starting with a remark made by famous mathematician J. Dieudonné. He has written 4 volumes of analysis book, which almost every mathematics library will be having. He is famous and therefore his words carry more weight. There, in one of the reviews, this famous professor Dieudonné, French professor, is writing the following sentence. I quote, "The Hindu scholar Pingala may have known a method for Pascal's triangle, but the case is more cryptic. At any rate, it was known by the time of Halayudha, who may have lived in 900 AD. My quote ends here. Of course, he has written a full article on this. But let us first understand what he says in these 2 sentences. He is referring to 2 scholars who lived nearly 1,000 years ago, more than that. One of them is Pingala, another is Halayudha. Pingala is also known as Naga Pingala, and he has written a book. The book name is Chandas Sutra. That book is really not a mathematics book. It is a book on prosody, which is useful for poets. What are the conditions and constraints under which poems are to be composed? In that book, there is one very brief sutra. It reads as follows, Pare Purnam. It comes in the middle of some other sutras which describe mathematics. For example, how to convert a number from binary representation to decimal representation and back from decimal representation to binary representation. Such problems, which are very much needed in this day of computers, were discussed 1,000 years ago by Pingala. Actually, Halayudha lived 1,000 years ago. Pingala lived more than 2,000 years ago. Pingala's name is a pre-Christian era name. Before Christ, Pingala lived and wrote Chandas Sutra. In that, he is giving some recurrence formula for these binomial coefficients. Of course, he doesn't call them by the name binomial coefficients, but he has a method of writing the next line of numbers from the previous line of numbers. Now we know that these are precisely the binomial coefficients. Now, What does Dieudonné, the famous French mathematician of our times, say about that? He says this Hindu scholar may have known a method for Pascal's triangle. May have known. We are not sure, because his words are very cryptic aphorisms. They may mean this or they may mean something else. But for his book, in India, through several centuries, there have been many commentators. We may be surprised that this one book has received dozens of commentaries, because this is a book of science 2000 years ago. And one of those commentaries is by one person called Halayudha. Halayudha lived around 900 AD, and in his commentary, he gives this interpretation of Pingala's Sutras. Sutram says Pare Purnam. Halayudha interprets that in the Pascal's triangle, the next line is obtained from the previous line by the method called Purnam or completion, which means, according to this interpreter Halayudha, that you have to add two consecutive numbers there and write it in the next line. We have to agree with Dieudonné that whether this is explicit, it is of course explicit in Halayudha's commentary, but it is not that explicit in Pingala's work itself. Therefore, we agree with him that the case is more cryptic, but at any rate, even to say that 1200 years ago, Indians were dealing with binomial coefficients, that itself is a great achievement. If it is not there for another 1200 years ago, it doesn't matter. Now, a few words about this professor, French mathematician Dieudonné. The word Dieudonné is something similar to the word Devadanam, which is used as a name in India in several places. Devadanam in French has become Dieudonné. Dieudonné was born and brought up in Lille. He was having a short stay in England. In England, he learnt algebra. In 1924, he was accepted for the École Normale Supérieure, where Andhra Vail was a contemporary. It is good to recall at this stage that Andhra Vail visited India also, and he took up a professor in one of the universities in India. Dieudonné began working conventionally enough in complex analysis. In 1934, he was one of the group of Normalians convened by Weil, which would become Bourbaki. Many of us may be aware of the name Bourbaki. Actually, there is no person by the name Bourbaki, but there are so many books authored by Bourbaki. People were wondering how this person, Bourbaki, is able to bring out so many abstract books in mathematics in short span of time. Later, it came to be known that Bourbaki is not one single person. It is a group of mathematicians working under that pseudo name. Anyhow, it remained a mystery for several decades, and Bourbaki is admired for developing mathematics like anything. And in that Bourbaki group, this professor is also a member. He is notable for research in abstract algebra and functional analysis, for close involvement with the Nicholas Bourbaki pseudonymous group. Pseudonymous means it is, you have heard of the word anonymous. This is pseudonymous, something similar to it. Not that it is not, their name is there, but it is a pseudonym. And the elementary geometry algebraic project of Alexander Grothendieck. He is also known as a historian of mathematics, particularly in the fields of functional analysis and algebraic topology. His work on the classical groups, he wrote a book in French language. It was published in 1955. And his work on formal groups introducing what now are called Diyodhane modules, had a major effect on those fields. I'm saying all these things because, first of all, we should be able to admire Diyodhane. If such a great person, Diyodhane, is saying that thousands of years ago, India was well developed in mathematics, then his words carry more weight than anybody else's. I happened to actually look into the Sanskrit book written by Halayudha. It was available in a library in Kerala. And I copied the passage from there, which describes the Pascal's triangle entries where the binomial coefficients are entered. The passage starts with the words Uparishtat Ekam Chaturashra Koshtam Likhitva and so on. I'm not going to read the entire passage. I have not even copied the entire passage here. But from that book, I have copied for my use the entire Sanskrit passage which describes the Pascal's triangle and also the Pascal's identities there. How the Pascal's triangle is drawn is described in these sentences, which are in Sanskrit here. And when this is known to the world, particularly outside India, admiration came from all quarters. You may have heard of a Stanford University professor, Donald Erwin Knuth. He is famous. He is familiar to all of us because his books are prescribed as textbooks in our departments of computer science. Yet 2 or 3 decades ago, every university in the world, hundreds of universities were prescribing Knuth's book as textbooks for algorithms. But now it is not so. Now, even in the universities where I serve, the books are different. At that time, when I was at University of Hyderabad, our University of Hyderabad, as well as many other universities in the world, were using his books. He is such a renowned computer scientist. He is now the professor emeritus of the art of computer programming at Stanford University. He has been called the father of the analysis of algorithms. That person of that fame says, not only says, he writes in his famous textbook the following sentences. His book title is Fundamentals of Algorithms. Dr. Donald Knuth writes, the binomial coefficients have a long and interesting history. The earliest known appearance of binomial coefficients is in a 10th century commentary due to Halayudha on an ancient Hindu classic, the Chandas Sutra. That is, I'm stopping the quote passage now, discontinuing it, pausing it, and explaining what Donald Knuth is saying. Long ago, more than 2000 years ago, there was a book in India by the name Chandas Sutra. For that book, there have been many commentaries. One of the commentaries is by Halayudha, which came as late as 900 AD. That is, the commentary itself is 1000 years or more later than the original book. In that commentary, he calls it as 10th century commentary. There, binomial coefficients have been described. Not only that, he says this is the earliest known appearance in the world. In the world, there have been many ancient civilizations which have shown some advancement in mathematics, but in none of other civilizations we find binomial coefficients as we find in the ancient Indian civilization. Not only that, now I am continuing the quote from Donald Knuth's book. In about 1150, this is the 12th century, the Hindu mathematician Bhaskaracharya gave a very clear exposition of binomial coefficients in his book Leelavati. Quote ends here. In Leelavati book, which is very much available in the original and also in English translations nowadays, in chapter 4, section 6, there is there is a section on binomial coefficients. Bhaskaracharya of 12th century was not only a mathematician but also a poet. Therefore, even the mathematical problems he will give as poems with rhymes and alliterations, so that his students will like mathematics very well, because it is coming in the form of poem. They will by heart those poems and solve those mathematical problems. And some of those mathematical problems involved binomial coefficients. Okay, this is how a tribute is paid in this world-renowned book to the Indian mathematicians of the lore. I'm passing on to some other book. This book is also as old as that, older than Bhaskaracharya's book. This is from a book titled Para Sangrahamu from Karnataka state, authored by one Mahaviracharya. This Mahavira is different from the founder of this Jain religion, Mahavira Vardhamana. This Mahavira is different, but he has written a very famous book that has been famous from those days. 1000 years ago, when Indians learnt mathematics, what were their textbooks? Their textbooks were Mahaviracharya's Ganita Sara Sangraham and Bhaskaracharya's Leelavati. These were the textbooks in those days. There, I am reading one passage. As I said earlier, it has been in a practice in India that even mathematical formula are written as verses or stanzas or poems. Mahavira is not an exception. He also writes a poem. This poem gives the formula for N choose R. Ekadyekottaratah padamurtva kramotkramasah sthapya pratilomagnam pratilomagnena bhajitam saram. This is what the poem, the verse is. This is verse number 218. You should remember that there are 1000 verses like that in that book. Now, the translation, English translation of this is as follows. It has been translated into many languages. One of them is English. In fact, about the English translation of this book, which happened in 1912, that is 100 years ago, that itself has a history. There is a story behind it. We are going to see that story also today. This verse means the result is the quotient of two products, namely the product of numbers in the reverse order and the product of numbers in the direct order. First, in the numerator, put numbers in the reverse order. Start from the number that you want, n. Then reverse order, next number n minus 1, next number n minus 2, and so on. How many? Depends on how many objects you want to choose. If you want to choose R objects, like R terms there. Then what is the denominator? It is the product of numbers in the direct order, starting from 1, 2, 3, etc. This is the formula that he gives in words, not in symbols. In symbols, it means n into n minus 1 into etc. divided by 1 into 2 into etc. R. That is the formula for n choose R given in this particular book. About the author of the book. Mahavira was a 9th century Jain mathematician from Mysore, India. His book title is Ganita Sara Sangraham, and it revised the earlier textbook used in India, The earlier book was Brahma Sputa Siddhantam of Brahmagupta. When Mahavira's book became popular, it replaced that. This author Mahavira was patronized by the Rashtrakuta king Amogha Varsha. Amogha Varsha is the name of a king who patronized Mahavira, that is, who helped Mahavira financially so that he can devote all his time to his mathematics. This Mahavira separated astronomy from mathematics. Before him, including in the book Brahma Sputa Siddhanta, mathematics was a part of astronomy. But from Mahavira's times, it became a separate subject. I have said that this formula is available in Mahavira's book, and it goes beyond doubt. Everyone accepts it. But some people argue that it is available even earlier. There is one book which is more famous than even Mahavira's book. It is called Brihat Samhita, older and more popular, written by Varaha Mihira. In that book, there is a passage which, according to some translators, means that it is the formula for n choose r. The passage is this: Purvena Purvena Gatena Yuktam Sthanam Vinantyam Pravadanti Sankhyam Ichha Vikalpai Kramashobhiniya Nite Nivritti Punaranya Nitihi. It is not very clear whether this gives the present well-known formula for n choose r. Therefore, I am reading its English translation because the entire book has been translated into English. For this passage, the translation comes as follows. Write the numbers 1, 2, 3, etc. n in the direct order and in reverse order, one below the other, and retain according to the requirement. That is, if you want r objects, then take r terms only. This gives the formula n into n minus 1 into etc. r terms there in the numerator, divided by 1 into 2 into etc. into r in the denominator. This translation is by one expert professor, Professor S. Madhavan from Kerala. I had an opportunity to meet him and discuss with him about the validity of this translation itself. He convinced me that the word Vikalpa is always coming in Sanskrit for combinations, and therefore this can only be the meaning of this formula. However, sometimes things are very revealing and disputable, and sometimes we may have to wait and see. This is a page of Brihat Samhita, 1946. It has been published. About the book Brihat Samhita itself, here are a few words. It is an important contribution of Varaha Mihira, and many of us think that it is an encyclopedia. Encyclopedia means different subjects are put together and briefly explained in a single book. This Brihat Samhita is like this. It covers wide-ranging subjects of human interest. There is a chapter on astrology. There is a chapter on planetary movements. There is a chapter on eclipses, on rainfall, on clouds, on architecture, on the growth of crops, that is agriculture, on the manufacture of perfume, that is cosmetics, on matrimony, on domestic relations, on gems or Ratna Pariksha, on pearls or Muktahara, and on rituals. So many chapters are there. It is not a book on a particular subject. It seems to be the compilation of all wisdom known at his time. The volume expounds on gemstone evaluation criterion found in the Garuda Puranam. It elaborates on the sacred 9 pearls from the same text. It contains 106 chapters. And its name itself, Brihat Samhita, that itself means great compilation. All scientific results known in his period, he has compiled in a single book. In such a great book, this formula for N-choose R is also available according to some experts. Nearly 1000 years ago, in India, mathematics was well developed, but this particular chapter on permutations and combinations, which they call as Vikalpas, this was found to be difficult. Not as easy as the chapter on arithmetic operations or chapter on polynomials or chapter on equations or chapter on theory of numbers. All of them were comparatively, relatively easier than this particular chapter. In fact, Bhaskaracharya, in one of his verses, says that this chapter is going to be difficult. Na guno, na haro, na kritihi, na ghanah prishtas tathapi dushtahanam, garvita ganaka vatunam, syatpato vashyam, ankapashesmin. Ankapasha is the technical term, the name that this mathematician gives to this chapter. Permutations and combinations, what we call by that name now, it is called in his book as Ankapasha. What does he say in this verse? Not multiplication, not division, not squaring, not cubing, but it is permutation and combination that certainly pulls down the wicked and arrogant boys in mathematics. He himself is a great teacher. He had all kinds of students in his class, and some of the students were arrogant also, so arrogant that they can solve all these problems quite easily. But even they are pulled down when they come to learn the chapter on permutations and combinations. That is the experience of that teacher, which he includes in this book itself. We have so far heard about many Indian textbooks, 3 of them particularly. One, Mahavira's Ganitasara Sangraham, second, Bhaskara's Leelavati, and third, Varahamihira's Brihat Samhita. Among these, Mahavira's book nowadays has more outreach because that book has been translated into many languages. In 870 AD, it was written in Sanskrit language by Mahavira. In 1050 AD, a Telugu version of that book was brought by Pavaluri Mallanna, and for several centuries, that was the textbook in the Telugu state for all mathematics students. In 1912 AD, first English translation of the book was made, brought out, published by one Professor M. Rangacharya, and there is more story to it, which we are going to see a little later. In 1963, Hindi translation of the same book was made by one L.C. Jain. In 2000 AD, Kannada translation was made available by one professor who is known to our group, Professor Padmavatamma. In 2003, Telugu translation of the same book was published by Telugu Academy under the leadership of Professor P.V. Arunachalam, who was a Vice Chancellor at Dravidian University, Kuppam, and who is well known as a mathematics professor. I'm saying so much to say that Mahavira's book is so popular. And in that Mahavira's book, beyond doubt, this formula is given. Formula for N choose R. Therefore, a little clarity is now available about the history of this formula. But then some questions remain. Do all historians in the world agree with this? That is one question. Even after seeing it in the book of Mahavira, can we say that he discovered it first, or was it already known? This is second question. Mahavira is only post-Christian era. In the pre-Christian era, was it known to some extent or not? This is a third question. Were there improved formulae later in Sanskrit? This is the fourth question. Did the research in mathematics and permutations and combinations stop with this particular formula, or was it further developed? For all these questions, we will try to see our answers in the remaining short span of time. First, among so many books available in our library on the history of mathematics, one that is very famous is a 2-volume book by Professor Smith. It is available in many libraries, including our University of Hyderabad library. I have gone through that book, and I really do admire Professor Smith because he has compiled from so many countries, from Egypt, from China, from India, and so on, in the ancient period, which formulas were available in which countries. Kudos to him, but a little later I'm going to criticize him. Now, I'm reading one sentence from some other book about this Smith's book. Here is a quote. The general formula for n choose r has wrongly been attributed to Herigone, Herigone. That's what Smith's book says, that he discovered this formula. It is wrongly attributed by Professor D. E. Smith in his History of Mathematics, published in 1925. This 1925 book gives a wrong history. Ironically, 13 years earlier, this happens in 1925, 13 years earlier, that is in 1920, Professor Smith had written a foreword to Mahavira's Ganita Sara Sangraham, published in 1912. From this, what do we know? The moral of the story is that even though Professor D. E. Smith is a well-recognized, most admired historian of mathematics, he has not been honest. A historian, especially of science, should have an unbiased mind, as also a thorough consistency in his presentations and assessments. Why does this author write like that? Why does he criticize Smith? Because in the 1912 book itself, Smith knows that this formula is available in Mahavira's book. Mahavira lived several centuries before Herigone. Then how can D. E. Smith write in his book on history of mathematics that this formula is discovered by Herigone, a European mathematician? He has deliberately suppressed the facts. That's what this author is feeling. This quote is taken from the book Indian Mathematics and Astronomy, Some Landmarks. Author's name is S. Balachandra Rao. This is published in Bangalore. It is very popular book. We all like this book very well. In the next slide, I am showing one page from this translation of Mahavira's book into English, 1912 book. There is a purpose in showing a copy of this page. The purpose is, it starts after the preface with the introduction by Dr. David E. Smith. Smith has written an introduction there to Mahavira's book. Therefore, he certainly knows that Mahavira has given the formula for n choose r. Still, he has chosen to ignore it in his History of Mathematics book. That is what makes him not very honest. Not only we, many European mathematicians are also saying that. Now come to the question. Who discovered the formula for n choose r first? This book says, Balachandra Rao's book says, Mahaviracharya discovered it. It was in the 19th century. He writes, the credit of giving out this general formula for n choose r for the first time in the history of world mathematics goes uniquely to Mahavira. Thus writes Dr. S. Balachandra Rao. But it has been contended. Others are saying Varahamihira lived much earlier than Mahavira. In the 5th and 6th century, he lived. Maybe he was the first who found this formula. There are some others who still say that it may be known in India still earlier, because Varahamihira says he only compiles the known results. He never says that he is discovering that result. And if you look into more earlier books available, particularly maintained by the Jain school, the Jain religion has maintained many mathematics books of the past. Some particular cases are available in 200 before Christ also. Particular cases means find 5, choose 3. Such problems are available. But whether the general formula was known is not clear. Now we come to the crux of this criticism. There is an injustice. Who says, if you make a Google search, if you go to the website, there is a site called MacTutor History of Mathematics. That website is maintained by 2 Scotland professors. One of them is Ian G. Pearce, is our contemporary. He writes the following sentence in that website. It seems to me an incredible injustice that the work of Indian scholars is not rewarded with a much more prominent place in the history of mathematics. What Pearce says in this sentence is, in history of mathematics, we are doing injustice to India. Even after knowing that many of these formulas were already known in India thousands of years ago, in our history books, we are not writing it. Therefore, Indian scholars are not rewarded as they should be. He even goes further to write in his website that some historians are arrogant. Even after knowing that mathematics was much more developed in India 1000 years ago, they do not highlight it in their own books of history of mathematics. He says it is not only ignorance, but also arrogance. That website, MacTutor website, is a famous website. It became famous because even the modern day mathematics results are included there. And therefore, many are seeing this comment made by Ian G. Pearce. Now I move on to a more modern website again. This person is not as famous as the persons that I have quoted so far. Among the mathematicians also, Diodoné is very famous, Andrew Weil is very famous, we have quoted from them. Among the computer scientists, Donald Knuth is very famous, we have quoted from him. But even though the person whom I'm going to quote later is not as famous, I quote him just to see that even others, the day-to-day workers of mathematics who may not have contributed much to mathematics, even they know that mathematics was well developed in India than in other countries in the ancient civilizations. Here is a quote from Mark Jason Dominus. I ran across the algorithm last year. He is referring to some algorithm related to binomial coefficients. And he found it in an Indian book of past. 1000 years ago, Indian books are giving algorithms to find binomial coefficients. While I was reading the Lilavati, a treatise on arithmetic, we have already seen about this book Lilavati of Bhaskara. which was a mathematics textbook in India before the colonial rule. This Lilavati is written about 850 years ago in India. I find in this book an algorithm. This algorithm is simple. This algorithm is ancient. This algorithm is efficient. This algorithm is convenient. He asks, why isn't this better known? We are seeing many algorithms, but this particular algorithm has all the good qualities that an algorithm requires. This algorithm is to find n+1 choose R if we know n choose R the previous row in the Pascal's triangle. Very easy algorithm, very effective algorithm, but we are not using it, we are not popularizing it, we are not even making it known to the public that India has contributed this much in mathematics. The main idea of the algorithm is this. I took this from his website. His website is called www.prover.com. Algorithm is simply this. n+1 choose k+1 can be calculated easily. It is just to take the previous one, n choose k, multiply it by n+1 by k+1. That's all. It is a recurrence. If you know nck, then the next one you know, n+1 choose k+1. This is in a article titled How to Calculate Binomial Coefficients. Up to now, we have seen quotes from different mathematicians, some of them ranging from such famous mathematicians as Duryodhana, such famous computer scientists as Donald Knuth, and not so famous website holders as this person who has the website named the University of Discourse. From all of them, one message is common. That message is, thousands of years ago, India was very much advanced in mathematics. It was good in binomial coefficients. It was great in developing algorithms. It has produced Pascal's identities there and so on. Even after knowing this, some of the historians of mathematics have not cared to include this in their books. But it cannot go on. Now, knowledge cannot be suppressed. It has become in open domain, and therefore it is now available in many websites that Indian contribution to mathematics is far superior. If even after this, the historians of mathematics do not include it, it is not ignorance, it is arrogance. That is what Ian Pierce said. So far, we have chosen only two formulas for n choose R. One is the formula factorial n by factorial R into factorial n minus R, and another is a formula known as Pascal's identity, and shown that their history extends far beyond to nearly 3,000 years ago, Pingala Naga's period. In his book, it is not very clearly stated. In the commentaries from 900 AD onwards, these formulas are very clearly stated. With this, I stop my talk today. Once again, I thank the organizers for giving me this opportunity, and I thank the hundreds of participants who are listening to this talk patiently. Thank you.
Thank you, Professor Kannan, sir. Any questions from the participant side? Would like to interact with today's invited speaker? Any questions from participants? Would like to interact with our invited speaker?
I'm stopping sharing.
Yeah. Any questions? Sir, there is no any more questions from the participant side.
Yes.
So I thank you very much, sir, for accepting our invitation in spite of your busy schedule and coming forward, deliver an invited talk. I know how much you're busy. So even also by requesting our side, without denying, you are accepted an invitation just to deliver a very good talk, sir. I think everyone, I think who are attended today, your invited talk, I think history of mathematics, particularly how we can go for like N-chooser, like an history of N-chooser, given elaborately will explain it. Through that, at least our young generation and who are working in the mathematics field, at least they will enlighten by your, at least they enlightened by your talk, as well as they'll come across, I think, what is history behind it, our mathematical concept. So they will elaborate, hence they will take it granted, and they will go to know it more about the history of our mathematics and their mathematician contributions. And also, I feel that you're also, I feel that personally, you're also like our mini Rahmanjan. So you have that more capacity of analyzing things and delivering a very good talks in the various levels. A very complicated content also you can deliver in a simpler way, understanding way to the common audience also. So I thank you very much, sir, for delivering our excellent talk. And my personal request is, I think we were unable to bring you to the offline mode, but next time we try to invite you to come to CUK physically. Kindly accept our invitation. Kindly you come to visit our CUK, as well as you give proper guidelines to us, as well as you can give proper guidelines to our MSc students and the PhD students, so that everyone will get benefit by you. So thank you very much, sir.
Sure. Thank you.
Thank you very much, sir. Just we will sign up, sir.
Ah.
Thank you.